Welcome back, everybody. In this section, we start looking at rates of change for functions, which is an idea that is related to the slope of a line, kind of, and then also looking at the behavior of graphs of functions. So we're going to start by looking at rate of change, which has to do with slope. So to do that, we want to review slope just a little bit from your intermediate algebra studies. So if you have a straight line with 2 points, x1, y1, and x2, y2 on it, then we can calculate the slope as the change in y, let's just say y change, divided by the x change. And it doesn't matter what order you put the points in. So we'll have y2 minus y1 on the top, x2 minus x1 on the bottom. And that's a formula for slope. You'll see this written in books as letter M for slope, and that's the M that you see when you write the equation of a line y equals mx plus b, right? All right, so what this section has to do with, or this part of this section, is kind of extending that idea to look at functions that are not necessarily straight lines, because of course the slope idea had to do with linear functions. So we want to define the idea of the rate of change of a function. A rate of change describes how a output quantity changes relative to the change in the input quantity. The units on rate of change are output units per input unit. So basically, if you think of miles per hour, feet per second, a printer that prints in pages per minute, 8 people per table, anytime you hear a per, there's a rate that is being discussed, and we can think of a rate of change. The average rate of change, which is what we're talking about here, between two input values is the total change of the function values, that's the y values or output values, and that's divided by the change in the input values. So here it's f of x2 minus f of x1 divided by x2 minus x1. And this should look like a lot like our slope formula that we had above, y2 minus y1 over x2 minus x1. And it's really similar. The output, remember, to a function is a y coordinate or y value. So it's really just kind of a relabeling, taking into account that f can be just a general function and is not necessarily a linear function. The symbolism on the left side takes a little bit of explaining. This little triangle next to the y, next to the x, is a symbol. It's a Greek letter, delta, that stands for the change in a quantity. We'd rate the ratio out loud as delta y over delta x, or the change in y divided by the change in x. That notation is used especially in situations where we don't especially care which 2 points on a line or on a graph are being used. We just want to express that ratio of how much y change accompanies a certain amount of x change. Okay, so the formula, and this is an important one to know going forward, the change in f, that's another way that you'll see it, not just change in y, you might see change in f divided by change in x. Okay, so let's try it with this function. We have this function, let's just call it f of x here, and we want to figure out the rate of change from x equal 2 to x equal 5. So we'll have f of 5 minus f of 2, and that will be divided by 5 minus 2. So let me locate those 2 points on the graph. So we have an input value of 2 and an input value of 5. So f of 5 is 7, and then f of 2 is 3. And then down below we have 5 minus 2. So 7 minus 3 is 4, and 5 minus 2 is 3. So overall, that slope is going to be 4/3. This is the steepness of a line segment that joins those 2 points. Okay, that line, by the way, is sometimes called a secant line. you may hear me refer to that as a secant line, and that's why. Okay, so we've calculated the average rate of change for that function over that interval. Okay. Notice that for a linear function, the slope is constant. And that's kind of a defining characteristic for a function, is that it has uniform or constant slope. Here, the average rate of change for this function between the points 2, 3 and 5, 7, that would be different from the slope between 2, 3, and let's say 4, 4, right? So the average rate of change over the interval from 2 to 4 is different from the average rate of change from the interval from 2 to 5. In fact, let's go ahead and calculate that. It should be less. This purple line looks like it's less steep than the black line is, but let's go ahead and calculate. So we'll have f of 4 minus f of 2 divided by 4 minus 2. The change in the y values this time is just 1. Here the output was 4, the output here was 3, 4 minus 2 is 2. Okay, so this time the slope only worked out to be 1/2, or the average rate of change worked out to be 1/2. Okay, so we have another example of that. Okay, this one, there's kind of a story with it that might help make this a little bit clearer. Suppose that we have an 8-inch candle. It's going to burn at a non-constant rate in such a way that its height in inches after t hours is given by this function, h of t, height is at time t, and it'll be 8 over t plus 1, where the input t is in hours and the output h is in inches. So I used the computer to produce this little graph. It's pretty clearly not a linear function. Horizontal axis time, vertical axis height in inches. We want to know how fast the candle is burning on the interval from 0 to 2. So let's do that. So from the interval 0 to 2, that means we want h of 2 minus h of 0 divided by 2 minus 0. H of 2 will be here on the graph. We can plug it into this function though, right? Let's put in 2. 8 over 2 plus 1 is 3. That's 8/3. And then h of 0, well, that's the initial height of the candle, right? It was initially an 8-inch candle. And then down below we have 2 minus 0. Okay, so a little arithmetic to do here. 8/3 minus 24/3. That's just divided by 2. So we will have negative 16/3 divided by 2, which is negative 8/3. All right, so that's the average rate of change over that interval. And that is the slope of that little secant line between those 2 points. Okay, next up, we'd like to figure out how fast the candle is burning over the interval between 2 and 4. So that will be h of 4 minus h of 2 divided by 4 minus 2. H of 4, 8 over 4 plus 1, that's 8/5. And then we'd calculated h of 2 before, that was 8/3. And then we're going to divide through by 2. Okay, so once again, with a little bit of fraction arithmetic, common denominator for 5ths and 3rds will be 15ths. So we'll have 24/15ths. And then here, a factor of 5 needs to be introduced. So we'll subtract 40/15ths. And then that's divided by 2. Okay, so then 40 minus 24 is 16. So we'll have negative 16/15ths divided by 2. So that will be negative 8/15ths. Okay, So that is still negative, which makes sense. The candle is getting shorter over time, right? As time increases, the length of the candle decreases. But 8/15 is smaller than 8/3, or smaller in absolute value than 8/3 is. And that makes sense if you take a look at the graph, that the function is less steep between 2 and 4 hours than it was between 0 and 2 hours. Okay, and then finally, let's figure out how quickly the candle is burning on the interval between 0 and 4 hours. So we'll have h of 4 minus h of 0. And then that's divided by 4 minus 0. H of 4 we calculated above here as 8/5. H of 0 was the initial height of the candle, which was 8 inches. And then we're doing this over a 4-hour period. Okay, so 8/5 minus 40/5, that's divided by 4, negative 32/5 over 4, that will be negative 8/5. Okay, so then that is bigger than negative 8/15, but smaller than negative 8/3 in absolute value. And that makes sense because here we're looking at the steepness over that interval. Sorry, I missed twice. There we go. So this one has slope negative 8/5. This one, middle one was negative 8/15. All right, so the candle burned most quickly in the first 2 hours and less quickly in the second 2 hours. The average over the first 4 hours was in between the first 2-hour average and the second 2-hour average. The purpose of this example is really to just get used to working with that formula for average rate of change, and to recognize that for a function that's not linear, you're going to get different values. For a straight line, of course, you get a constant value for slope, regardless of where you are calculating. All right, so we have one more example. Here, I have another, this one is taken from a different book, another way of expressing the definition of average rate of change. I had written this down basically before. This book does use the wording secant line. I didn't see it in our textbook. This is just another graphic that kind of illustrates how that calculation is done. Okay, here we have the square root function. And then the question originally was to find the average rate of change over the intervals 1 to 4, then 1 to 9, and then 4 to 9. So I did the calculations here. So this will be in the notes and you can see how that is working. You can see that the values for the average rate of change are different. And what it is still that they're expressing is how steep the graph is. And we'll use that here on the next slide in just a moment. So take a look at these calculations. Let me know if you have any questions on that. Okay, so we're going to use some of that here with this square root to help produce this graph for the square root function. It says, let f of x equal square root of x. Find the equation of the secant line to the graph of f at x equal 9, and use it to estimate the square root of 8. We'll graph both f and what's called its linearization. So we want the, let's go ahead and put the graph of the square root of x up there first. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. I'm going with values I know, right? The square root of 9 is 3. And then we could, of course, keep going. Okay, so there's a rough sketch of the square root function. Okay, so we want to find the equation of the secant line at the point x equal 9. So right there at the 0.93. So we want the average rate of change will tell us the slope of this secant line. So let's go ahead and calculate. So the thing is that we need 2 points, right? So we want to estimate this secant line at 9. So we should use 2 points that we know. So let's try 4 and 9. I chose 4 because it was one other value that I knew the square root of. So there's 9 minus 4. All right, so now if we draw a line between the point 42 and 9,3, we'll get basically this pink line. That line has slope 1/5. Okay, you can see from our graph that the straight line, of course, is straight. The square root graph is curved, but pretty near the point where we are constructing this line at 9, the two are close together, and we'll see that we can use that to approximate our function. So let's finish finding the equation of the line. So it has to pass through the 0.93 and have slope 1/5. Okay, so we want to find the equation of that line. So we'll use the slope-intercept form. We know that it has to have slope 1/5 and pass through the 0.93. So when x is 3, y will be 9. So then we can use that to calculate the y-intercept. So little fractions. Here we're going to have 45/5 minus 3/5. That's our b. 42/5 for our y-intercept. So then our line, y equals 1/5 x plus 42/5. Okay, so what does that give us? Well, the equation of this line, as we saw, the line is pretty close to the graph of the function. And so we can use it to help us approximate or estimate this square root of 8, which was part of the question. So let's do that. And I don't know what the square root of 8 is. I know that it's less than 3, because the square root of 9 is 3. And I know it's bigger than 4, because bigger than 2, because the square root of 4 is 2. But other than that, how close can we come? So let's substitute 8 into here. Okay, so this will be 8/5 plus 42/5, and that's 50/5. And that doesn't seem right. I messed up somewhere. Let's see. Okay. All right, so let me see. So how do I know that's wrong, right? Because that y value should be nowhere near 10. So there's an issue there that I'm going to have to fix. So give me a second to do that. All right, so sorry about that. I made a kind of silly mistake. In here, I had intended to substitute in the 0.93 in finding the equation of the line. And I wasn't very careful because instead of putting in the x where the x goes, I put the y in. So I had put the y value of 3 where I should have put the x, and I should have put the y value of 3 here. Instead, I'd put the x value of 9. So I'm going to go ahead and fix all that. So you'll see this change here right now. All right, so sorry about that, but this we've got now is repaired and is much better. Our slope of our secant line is 1/5, and our y-intercept turned out to be 6/5, which is a lot better. So now, if we want to use this secant line to approximate the square root of 8, we'll have 1/5 x, here our x is 8, and we're substituting it into this equation and calculating a value for y. So y will be 8/5 plus 6/5, and that's equal to 14/5. 14/5 is 2.8 if you like decimals better. And so we want to see using a calculator what the square root of 8 is approximately. So using my calculator, I have the square root of 8 is approximately 2.828. Okay, which is pretty good. And of course, given the fact that I was able to get the answer using a calculator, that begs the question, why did you go to all this trouble with the equation of the line and everything? Part of it is practice at coming up with the equations of the lines, and partly also is to reinforce this idea that this line that we generated using the average rate of change is a good approximator for the function near where we made that approximation. In other words, we saw that this was pretty good approximation for the square root of 8, but what if I wanted to try to use it for the square root of 100? Well, let's try. We have 1/5 times 100, that would be our x value, plus 6/5. The square root of 100 is 10, so 1/5 of 100 is 20. 20 plus 6/5, 6/5 is 1.2. So that would be 21.2, right? Which is pretty far off from 10. So that's the thing, is that the approximation is not as good further away from our where we built the approximation. So I'm going to bring up another. All right, so I've used the computer and a website called desmos.com/calculator to help us produce a nicer looking graph of the function we're working on. And you can see that close to where x is 4, sorry, let me change my axis scale a little bit. Close to where our approximation is occurring, our function is, our linear function is close to what the value for the square root is, because that's where we built our linear approximation. Of course, as you zoom out, you can see that the graph of the square root is really far from what the linear function is. If you did want to use this idea to help you do something like approximate the square root of 95 or something, then you'd be better off using like 81, square root of 81 is 9, and then maybe the square root of 100 is 10 to help you with something in the neighborhood of 95, right? So that was the big idea here. We really wanted not so much to figure out how to do square roots, because of course the calculator can do square roots much faster than this all was. The big idea was mostly how the average rate of change for a function is dependent on where on the function you're looking, unlike a straight line where it's like the same no matter where you look, and how you can use a linear function to approximate a nonlinear function. So this doesn't quite finish up this section 1.3 for us, but it does finish up this video. So in the next video, we'll look at something called the difference quotient and then some more attributes of graphs of functions. Let me know if you have any questions, and in the meantime, have a great day.